In this recording, we will work a few examples. Okay, let's start with a simple one. It is asking about the kinetic energy of a 0.1 kilogram baseball when the baseball is moving at a speed of 45 meters per second. It's an easy one since the kinetic energy is given by the expression 1/2 of mv squared. So all what we have to do is plug in the values. 0.1 kilogram times 45 meters per second, and that's squared. Notice that this is an actual speed of a baseball. That's, I think, the highest speed of a baseball that was recorded. 45 meters per second is a record speed for a baseball. Now, so when I calculate that, 45 squared is 2025. So times 0.1 divided by 2. So that's equal to 101 joules. Now this next question is asking us about the loss of gravitational potential energy of a baseball when it falls from a height of 2 meters. Okay, so now here, if it's going to fall from a height of 2 meters, that means it's starting here, it is going to end up here. There's going to be a 2-meter difference. Now, if we set our reference point at ground level, then our gravitational potential energy, our EPG is going to be mgh, with h being 2 meters. So then it's going to be 0.1 kilograms times 10 meters per second squared times 2 meters. So 0.1 times 10, that gives us 1 times 2, that gives us 2 joules. And then here at the bottom level, EPG is going to be equal to 0 because h here is 0 relative to ground. So our loss in gravitational potential energy, our change is minus 2 joules, but our loss is just 2 joules of gravitational potential energy. Notice that I would have found the same result if I used another reference point. For example, let me choose the ground as a reference point. I mean, the initial position as a reference point. Then EPG initial would be 0. EPG final would be minus 2 joules. I'm 2 meters below the reference point, so my h is going to be minus 2, and that's the way, it's the same expression as here, but with a minus 2, that's why I will get minus 2 joules. So I go from 0 to minus 2 joules, so my loss is still 2 joules. Okay, now let's take another expression. How much gain of gravitational potential energy would a 50 kilogram student gain when moving from the ground floor to the first floor, 5 meters higher? What's interesting in dealing with gravitational potential energy, you worry about the initial point and the final point. You don't worry about the path taken. Now, and when you worry about the initial point and the final point, you worry only about the change in height. You don't worry about horizontal displacement. Now, in this case, what do we have? We had a change in height of 5 meters. So the change in gravitational potential energy is going to be just mg times the change in height. So in here, we have m 50 kilograms, g 10 meters per second squared, and then change in height is 5 meters. So 50 times 10, 500. 500 times 5, that will give us 2500 joules. Okay, let's move on. We have a spring with a constant of 100 newtons per meter. It is compressed 10 centimeters. How much spring potential energy is stored in the spring? Okay, spring potential energy, EPS, is just 1/2 of kx squared. K is given here, x is given here, so we just plug it in, 1/2 of 100 newtons per meter times 0.1 meter squared. Okay, 0.1 is going to become 100th when I square it, times 100, that gives us a 1 over 2, so it's 0.5 joules. So actually this is a dinky spring. We need to have a bigger spring constant. Anyway, so it's just 1/2 joule. Now, by how much would the answer be different if it is stretched by the same amount instead of being compressed? It would not be any different. EPS is still 0.5 joules. Now, remember, this expression does not care whether it is compressed or stretched. All what matters is how far is it off the equilibrium position, and in both cases it's 10 centimeters, so we should get 0.5 joules. That's an important part. Okay. Now let's work this other example. We have a 0.1 kilogram mass that was tossed upwards with a speed of 25 meters per second from a height of 1 meter relative to ground. So it is tossed up from a height of 1 meter relative to the ground. What is the mechanical energy relative to the ground of the ball the minute it is tossed? Now, when we are tossing it, there are two things occurring there. At that particular point, so this is ground for us, this is the person tossing the ball, it's 1 meter above ground. Now, the ball at that position is going to have a gravitational potential energy. Since they tell us to measure it relative to ground, that gravitational potential energy is mgh. It is, in this case, 0.1 kilograms times 10 meters per second squared times 1 meter, which is just 1 joule. Now, tossing it is giving it kinetic energy. So that kinetic energy is 1/2 of mv squared. Now in this case, that's going to be 1/2 of 0.1 kilograms times 25 meters per second squared. Now, that's 625 for 25 squared. That gives us 31 joules. Now, what would be my mechanical energy? The mechanical energy is the sum of both EPG plus EK. So it's going to be 31 plus 1 joule. So it's going to be 32 joules. Okay, that's part A of the question. Now, the interesting thing, what's the mechanical energy of the ball when it is at the highest position? Of course, they didn't say it in this question here, but assuming no losses due to air resistance. Okay, in that case, mechanical energy remains conserved, so it should be 32 joules at the highest position as well. Now, the question then asks, what is the kinetic energy of the ball when it is at the highest position? Okay, the highest position is, that's when the ball momentarily stops. So its kinetic energy is actually equal to 0. That's the highest position. Now then, but then mechanical energy, we said, it is 32 joules. So what does that tell us about the gravitational potential energy? Since the mechanical energy is equal gravitational potential energy plus kinetic energy, since this is 0, that tells us our gravitational potential energy at that point is just 32 joules. Part A, part B. Now the third question, what is the highest position of the ball? So to find the highest position, all what we have to do is write the expression for the gravitational potential energy. It is mgh. And we know that it should be equal to 32 joules. We know what G is, we know what M is, so we solve for H. H in this case is going to be 32 joules over M, which is 0.1 kilograms, and times G, which is 10 meters per second squared. So this gives us 32 meters, which is quite high. This is the height relative to ground, by the way. Since the 32 joules is relative to ground. And that's because from the onset we calculated the mechanical energy relative to ground. Okay, now just to make sure, to be able to get this, I had to divide both sides by mg. So mg is cancelled here, and they were left here, and that's the way I got this expression. Okay, one last example. So we are still stuck with baseballs. We have a baseball here that was released from a height of 20 meters. What would be its kinetic energy just as it is about to hit the floor? Okay. Now, notice if we were going to work this problem the old way, we know the displacement, we know the acceleration, 10 meters per second squared down. So we know the initial velocity 0. So we have to find the final speed, the final velocity, and then solve for the kinetic energy after that. And that's not a bad problem, but it's not a difficult problem. To find the velocity, we can use the equation Vf squared minus Vi squared is equal to AD. We know A minus 10 meters per second squared. D is minus 20 meters, going down 20 meters. Vi is 0, so we solve for Vf. And then we use, for kinetic energy, Ek is 1/2 of mVf squared. So we plug in, actually, we solve for Vf squared and plug it in there. Okay, and that's an easy way. Now, the new way is to consider that when the ball is at the topmost position, it's going to have a kinetic energy. Okay, come on, right? Kinetic energy equal to 0, since it was released from rest. Okay, come on, buddy. And then it's going to have a gravitational potential energy relative to ground. That's going to be mg times h. H is going to be 20 meters relative to ground. So that's going to be m.1 kilograms times 10 meters per second squared. that's G, times 20 meters. So that's going to be 20 joules. So my mechanical energy at the initial position is 20 joules, 0 plus 20 joules. Kinetic energy plus potential energy, kinetic energy being 0, that's 0, plus potential energy 20 joules. That gives us a mechanical energy of 20 joules, which means just when it is about to hit ground, I should have the same 20 joules of mechanical energy. Now, at the bottom there, my gravitational potential energy is going to be 0, since I'm at a height of 0 relative to ground. So my kinetic energy is going to be fully equal to the mechanical energy. E kinetic energy is going to be E mechanical energy, so it should be equal to 20 joules. If you have solved it the other way, you should be able to find the same answer.